Okay, welcome back. Now, so far what we have discussed is that we have evolved the Prandtl-Meyer function and we have found that the relationship something looks like this. The right hand side is the big expression. Generally, this whole expression is not solved. This expression based on each Mach number, which is a function, this Prandtl-Meyer function, which is denoted by nu, is a function of Mach number at various Mach numbers and given gas, that is for our case let us say air, the gamma is given, and based on this Mach number these new values are calculated and tabulated against each Mach number. Therefore, for every particular Mach number, if you have you can calculate the nu. In turn, if we see that the relationship something like this, for each value of Mach number there is a specific Prandtl-Meyer function nu, and which can be added or subtracted, which we will see just now, and plus a constant. Eventually this kind of relationship for let us say two particular values of Mach number, let us say Mach 1, if the Prandtl-Meyer function is nu, and for another case of Mach number 2 the Prandtl-Meyer function is nu. Then to calculate the Prandtl-Meyer function, the respective Prandtl-Meyer function for two case, what we can do using this relationship, we can see that this Prandtl-Meyer function can be calculated by adding or subtracting the value of theta, that is nothing but your deflection angle. Therefore, if you know the upstream Mach number, as in our case for a supersonic flow past the expansion fan, then across the expansion fan if the upstream Prandtl-Meyer function is calculated, then by adding or subtracting whatever the case is the flow deflection angle, we can get the downstream Prandtl-Meyer function, and hence we can come to know what is the Mach number downstream side, that is the downstream of expansion fans. Now it means here also we can see that the Mach number is a unbounded parameter, that is as low as 0 or to infinity. Here I am taking that let us say for a supersonic case the Mach number should always be greater than 1. Generally Mach number is an unbounded parameter which should be lesser than infinity but greater than 0, but we know that if the Mach number is between 0 to 1, then a shock wave cannot be created because this is a subsonic flow. However, for supersonic flow the Mach number is 1 greater than 1 and lesser than theoretical infinite. So therefore, I am considering the range 1 to infinity. In this range the Prandtl-Meyer function can be calculated as at Mach 1 we have just said that in this constant of integration the arbitrary constant is chosen 0 such that for a case m equal to 1. Hence on the left hand side the range of Prandtl-Meyer function nu is 0 here. However, for Mach number infinite or in the real sense very large, in that case the nu maximum can be calculated, and this value of nu maximum is found to be pi by 2 in the bracket square root of gamma plus 1 upon gamma minus 1 and minus 1. Now what I said just now that downstream Mach number, let us say I am representing nu 2, which essentially I mean it that at Mach number 2 Mach 2 at m2, and if I am calculating at Mach 1 that is m1 sorry, then plus minus theta. Now here theta or delta theta, that is the flow deflection angle. Now this is the case that when we consider minus sign and when we consider plus sign, let us say I am representing here minus and plus. So when nu 2 is equal to, I am considering nu 1 minus theta. This is required because when there is a continuous compression and which is such that it is isentropic compression process, then still the process is isentropic everywhere including the wall, near the wall, then the downstream function is obtained by minus of deflection angle, because still the flow is turning into itself. Whereas in the second case, when the isentropic expansion fans are formed with a continuous surface, or like this, where the flow is turned away from itself, therefore the downstream Prandtl-Meyer function is calculated while using nu2 nu1 plus theta, and hence this is called isentropic compression process, and this is isentropic expansion process. Now we are familiar now with different kind of waves. If we talk about that from the Mach wave perspective, and we just said that Mach wave and Mach lines are real in nature, where however the Mach lines are where the changes are finite but it is very small. These are replaced with characteristic lines, and these characteristic lines in the two dimensional picture as shown here can be given as per their direction. The nomenclature is adopted that if I am moving along the uniform flow direction, then the left running waves are like this and the right running waves are these, and so these lines are termed as left running characteristics and these lines are termed as right running characteristics. These characteristic waves, they intersect each other, and these characteristic waves are linear waves, and it is termed that after intersection also they do not lose their linearity, that is before or after the intersection where these characteristic waves intersect each other, they remain linear, and that is why they are called simple waves. And being the simple waves, the properties of these waves or conditions on each of one of these characteristic waves are constant, and they are simple, and hence they follow the rule nu2 is equal to nu1 minus plus delta theta. Whereas in the zone traversed by formed by these waves, this relationship is not valid, that is termed as non-simple region. The left running waves are generally given in compressible flows with a positive symbol, whereas the right running waves, which is moving like from bottom to top, this is given with negative sign. Now moving further, an important aspect, how these shocks and expansion fans intersect each other. Just now we have completed the how the Mach wave intersect each other, and we have seen that how the simple and non-simple regions are formed. Now what happens when the shock waves and expansion fans, or that is the shock and expansion fan, how they intersect each other? Let us consider this fact. Please note it down, like in this kind of figure where two real surfaces, a real surface at the bottom, let us say bottom flat plate is here, whereas there is a cowl generated oblique shock wave. Now this shock wave which go and incident upon the bottom flat plate is reflected back in the form of this shock wave. However, note that even though this kind of reflection is termed as like reflection, because whenever shock reflects from a solid surface, this is called like reflection. Unlike our previous discussion where the shock is reflected from an imaginary surface such as the jet boundary or the jet boundary, that is the flow coming out of the nozzle, that is called unlike surfaces, unlike reflection. However, still even that the oblique shock which is hitting at the bottom plate is reflecting back, but this reflection is not specular. The specular reflection means that the angle of incidence of the incident shock wave must be equal to the angle of reflection. However, this kind of reflection not being specular in nature, the beta and beta dash, where beta is angle of incidence and beta dash angle of reflection, they are not generally equal. It may or may not. Now, in this kind of figure, what I have drawn here, let us say Cowell generated shock is incident upon the bottom surface, and if the upstream Mach number is m1 here, when this flow comes and passes across the shock wave, the tendency of a shock wave to turn the flow toward the surface. Then this wave, let us say I am representing here this flow condition is through a streamline. Now what happens after passing through this oblique shock wave, that is incident shock wave, this flow streamline turns toward the surface. Now in this zone, let us say downstream of the oblique shock wave, the Mach number becomes m2. Now if we are considering this wave as the oblique shock weak in nature, then this m2 we have seen that this may be still supersonic, and since this is a oblique shock of weak nature, of weaker strength, then this m2 being still supersonic will be good enough in generating this reflected shock wave. And furthermore, after m2, this streamline which turns towards the surface, due to the presence of surface, this shock wave after passing this flow must be parallel to the surface again, so that the condition of parallel to the surface upstream and the parallel to the surface downstream should be made equal. That means whatever the turning take place original parallel, the second shock will reflect back, will turn back the flow, so that the upcoming and outgoing streams are parallel to each other. Now it should also be noted that both m and theta ahead of reflected shock wave, that is the Mach number as well as the flow deflection, are smaller than those of ahead of incident shock. That means whatever the condition m2 here and along with theta 2 is present over here, this is lesser than the upcoming stream. Now in that case, with respect to this specular non-specular reflection, what we find here, that when the Mach number is small, that is a lower Mach number, the angle of reflection is higher than angle of incidence, that is shock angle. Whereas for higher Mach number, it has been seen that the angle of reflection beta dash is lesser than angle of incidence. We should make a note of these 2 points actually at lower Mach number in contrast to higher Mach numbers. Now let us see what happens when the two shocks of different strength of opposite family intersect each other. The family concept means, it is termed here on a two-dimensional diagram in a two-dimensional flow. The family is abbreviated as, that is the on which wall or in which direction these waves are coming. Likewise the Mach wave, the left running and right running shock waves we can designate. Therefore if this is a parallel surface, two flat plates are kept a some distance apart. So now if the waves which are generating coming from this surface and this surface, lower surface and upper surface, if they have the equal strength, then they intersect at the mid zone or midline, and the flow velocity coming out of downstream of these respective shock waves will be also similar, and being as their strength are same, and in turn the vorticity generated in the both upper plane and the lower plane along this midline will also be same. That means the shock pattern as well as the flow pattern above and lower plane due to the left running and right running shock waves are symmetric in nature, But what happens when these waves are of unequal strength, that is their strengths are not equal? In that case, this scenario is depicted over here. Please take a note that this left running and this right running shocks of unequal strength, they intersect each other, let us say at this point. However, after intersection also, this shock waves is transmitting in this wave, and this shock wave, the left running shock waves, is also transmitted in this way. However, you can see that they are no more linear waves, that is they are not in the same direction, however they are slightly tilted respectively. What happens in this case, that since the strength are unequal, then the upper zone, that is along the mid plane, the upper zone the velocity and the lower zone velocity are different. In turn, the vorticity, that is the vorticity in this domain and this domain are also unequal, because the upper layer and shear layer have the different velocity and they start having the shearing action, and due to this shearing action, the upper layer vorticity content, that is entropy, and lower layer entropy are different, and hence what happens, due to their unequal strength, the pressure also downstream side are unequal. In such a case, the stream, rather than going parallel as in the equal strength case, it is shifted, let us say in this case I have represented upward, that is the stream will be shifted either upward or downward. In this case here in this figure I have shifted upward, and the shifting here is denoted by an angle delta. Now this shifting, where this dotted line represent the slip stream or shear layer, slip stream or shear layer. Now what happens in the second case, when the waves of unequal strength but same family, that means the surface is same which generates these oblique shock waves, and they are going to intersect each other. Note down that since the surface is same, however at various corners these oblique shock waves are generated. Since these are of same family, they do not intersect and pass, while if the AO is the first shock wave which is having higher strength than the shock wave BO, what happens when they meet at the point, let us say O, then this weaker wave, oblique shock wave, attenuates this shock wave and transmit into shock wave OC, whereas one reflected shock wave OE is also formed, and because of this unequal strength, the slip stream which should be parallel along the surface is generated something in the form of OD. That is, moreover these oblique shock waves AO and BO, that is they are not of having same strength, they cannot intersect, whereas they coalesce and they form a stronger shock wave in the form of OC. Now a third case, if we take what happens when an oblique shock wave of one family intersects with the expansion fans and both of them are generated from the same wall. One such case is shown here, that one corner of the surface, lower surface, is generating an oblique shock wave something like this, whereas the second corner where the flow is turning away from itself is generating the centered expansion fan which is shown here. When these expansion fans go and meet this oblique shock waves, they are reflected back, and this reflection again are not specular in nature. Rather than generating in this case as a slip stream, the whole domain becomes filled with vorticity content, that is the whole flow domain will be having a complete amount of disorder, a finite amount of disorder is present in this case when this oblique shock meets the expansion fan. Now The application of these shock and expansion fans, we will discuss about two important theories to analyze a flow situation, because though we have studied as a tool shock wave and expansion fan separately, but at any surface they are occurring together. One such case we have taken here, for example, let us say a diamond shaped airfoil which is having a very vital supersonic applications. Let us consider this is a diamond section of an airfoil section, and you can see here that the vertex angle is 2e to epsilon both at the forward vertex and the backward vertex, such that along the mid plane each side is making an epsilon angle. Now, if this airfoil section is kept in a supersonic flow, which is I have represented here m1, and m1 is greater than 1, then at the nose an oblique shock will be generated, something like this. Now, when the flow comes and meets the oblique shock at downstream side, this being weak in nature, still the flow is supersonic and it is moving upward. However, here at the nose, since from the parallel stream, uniform stream, it is finding a surface which forces the flow into itself, and hence the shock wave is generated. Whereas, come to this point, at the vertex what happens, the flow which was originally in this direction is meeting as a vertex here and point here, where sudden change in the surface geometry that is away from itself, that moves, forces the flow away from itself, and hence a centered expansion fan is generated because of sudden change in the surface slope. Same process is occurring at the downside also. When we call this as an airfoil, let us designate a lower surface and upper surface, or the pressure surface and suction surface. Now, what happens in this zone 1, let us denote zone 2, and in this zone 3. What we can see here, and finally the pressure at, this is a zone at 4. The shock wave at the nose compresses the flow to the pressure P2. The centered expansion fan expand it to pressure P3. Whatever the compression P2 is obtained here, this expansion fan relaxes the pressure and that pressure becomes P3, and the trailing edge shock wave further compresses the value P4. However, this compressing will be similar to P4, which is again back to same as P1, that is the free stream pressure. However, because of this compression and an expansion process, the forward, if I am drawing a plane from the mid point here, which divide the this airfoil into two halves, then the forward zone, which is having higher pressure than the rearward zone, the difference of pressure between the forward zone and the rearward zone gives a force in the uniform stream direction, and that we termed as drag. Now, since this airfoil is kept at 0 degree incidence angle, that is the alpha is 0 here. Now, we can write down the drag per unit span, that is the perpendicular dimension of this airfoil per unit span. We can write down that P2 minus P3, that is the forward face, upper one P2, and since this will be relaxed, P2 minus P3, and then if the thickness at the mid plane is T of this airfoil section, then we can approximately write P2 minus P3 times T, where T is the thickness of airfoil at the shoulder. Now, you can see it here that the cause of this pressure difference is this oblique shock as well as expansion fans, and since the pressure difference is causing this drag, and hence this kind of drag over this diamond airfoil section is termed as wave drag. Note that here even the inviscid flow where this kind of diamond section airfoil is kept in a supersonic flow, the wave drag is always present. Now, using the shock expansion theory, let us take one simple example to calculate the lift and drag coefficient. The simplest example, if in a supersonic stream, if a flat plate is kept at an angle of incidence alpha naught, then if the plate is kept like this, then what we essentially see that uniform parallel stream when it meets at this point, that is the leading edge of the airfoil, flat plate airfoil, then at this point, since the flow will be turning away from itself, by geometry we can see, hence at the upper portion, that is the suction surface, there will be a centered expansion fan will be formed, whereas on the downward side, that is at the pressure surface, an oblique shock will be formed when this flow traverses or flow passed over the parallel flat plates airfoil over the upper and lower surface. At this trailing edge of the flat plate airfoil, since again the flow has to be parallel to the incoming stream, and hence here the flow, the generated oblique shock will turn into itself, since the flow has to turn into itself, and hence an oblique shock will be formed. Whereas the opposite case occurs at the downward surface, since the flow will be moving away from itself, and hence then a centered expansion fan is formed. In this scenario, if we try to write down the lift and drag, considering the chord of this flat plate is C, the chord or chord length. In that case, using the trigonometry, simple trigonometry, what we can write down that the lift per unit span of the flat plate airfoil can be written as P2 dash, which is obviously a pressure surface and higher, P2 dash minus the suction surface pressure P2 minus P2, P2 dash minus P2 into C cos alpha naught. Whereas in the bottom side, in the drag side, D drag we are obtaining as, that is P2 dash minus P2 into along the stream direction we can write down C sin alpha naught. Therefore, by the lift and drag coefficient we can relate it lift upon the dynamic pressure half rho v square and C for a per unit span. Therefore, we can write down, replacing L here with the first equation, P2 dash minus P2 upon Q1 C cos alpha, whereas C is downside also, both will be cancelled out. Similarly, CD can be written as D upon Q1 C, and this can be written as P2 dash minus P2 upon Q1, and again C will be cancelled out from numerator and denominator, and hence it can be written as sin alpha naught. Note that in a supersonic flow we can write down half rho v square, and we can convert this that is the dynamic pressure half rho v square can be written as easily gamma by 2 p m square. That is what I have written here. Therefore, what we can find it here, that this shock expansion theory, a very simple flat plate application, can give some approximate values of approximate relationship of CL and CD. However, a closed analytical form cannot be obtained using this shock and expansion theory for a particular case. Therefore, what we do, that even though we can get some idea of this kind of or any surface, that let us say airfoil in a supersonic flow using the shock expansion theory, but since the inability of obtaining a closed form analytical solution, we take some more approximation. Assuming the airfoil to be very thin, then we can, and which is kept at very small angle of attack, and further the flow inclinations are also small, then shock expansion theory can be made by using approximate relations for weak shock and expansion fan, and this kind of theory which further helps in deducing the relationship for thin airfoil kept at a small angle of attack with a small inclination everywhere along the airfoil, then this kind of theory is known as thin airfoil theory, which leads to analytical expression for lift and drag. That is what essentially our objective is. Now, for a weak oblique shock, we have seen that when the shock strength for a weak oblique shock waves can be given as delta P upon static pressure P1 is equal to gamma m1 square upon square root of m1 square minus 1 into theta. Now, using the pressure coefficient definition, we can write down P minus P1 upon Q1 is equal to 2 by gamma m1 square P minus P1 upon P1. That means if we take this equation 1 and equation 2, that is the definition of Cp, we can write down Cp in terms of theta as Cp is equal to 2 theta square root of m1 square minus 1. That is, the pressure coefficient is proportional to the local flow inclination at any point on the airfoil section. Thus, when we have taken from the shock expansion theory point of view, now let us consider to find out the analytical solution, a closed form solution for this flat plate case again. Considering the same flat plate, a thin flat plate kept in a uniform supersonic stream, and since the oblique shock and expansion fan at the leading edge and then oblique shock and expansion fan at the trailing edge formed, what we can write down here that since Cp for both upper and lower portion, lower surfaces, that is the suction as well as pressure surfaces, we can denote using minus and plus, where minus sign denotes the suction surface and the plus sign denotes the lower or pressure surface. We can write down the Cp 2 alpha naught upon m1 square minus 1. This alpha naught is since it is a local inclination which we have seen in this relationship here theta, and for a thin flat plate, each point along the flat plate, whether the upper surface or the lower surface, each one is experiencing the same local inclination, and that is why I have written 2 alpha naught upon m1 square minus 1. Now, Cl and Cd can be obtained by writing Cpl, that is the pressure coefficient on lower surface which is higher, and the pressure coefficient on the upper surface, and resolving this difference into the vertical as well as horizontal component along the streamline direction. That is, I can write down Cl is equal to Cpl minus Cpu cos alpha naught, and Cd can be written as Cpl minus Cpu sin alpha naught. Now, since our approximation is that the inclinations are also small, in that sense when the alpha naught is small, then sin alpha naught becomes alpha naught, whereas cos alpha naught will be equated to 1. In turn, this Cl and Cd can be directly and readily obtained using this equation as Cl is equal to 4 alpha naught upon m1 square minus 1, whereas Cd can be written as minus plus 4 alpha naught square upon m1 square minus 1. And note down the aerodynamic center is at the mid chord of this flat plate airfoil. Now, second case, what we have discussed, that diamond airfoil, now consider that this is a thin diamond airfoil. That means all these inclination, that is 2 epsilon here, are also small along with the angle of attack. Since this case we are considering the angle of attack as 0. Therefore, if we found out that Cp expression is minus plus 2 epsilon upon m1 square minus 1. Please note down that theta, 2 theta is here replaced with 2 epsilon, because the surfaces of this thin diamond airfoil are straight in nature. So, each point will experience the same inclination along this or this, because both forward angle as well as the backward angle, rearward angle, they are same. Hence, I can write down the drag finally using P2 minus P3 again with the same logic over the upper surface is that P2 minus P3 times T, and this T I can replace using epsilon into C, where epsilon is the angle, and hence I can deduce this drag equation as 4 epsilon naught square upon m1 square minus 1. Now, let us take, we have taken a flat plate, a diameter airfoil section. What happens when an arbitrary airfoil is chosen, that is the airfoil with arbitrary shape? In compressible flow in the fundamental concept, this kind of general natured shaped airfoil is divided in such a case which can be readily obtained. Here a general shaped airfoil is considered as first a angle of attack alpha naught, let us say a flat plate. Second case is that this flat plate is given a angle of attack, that is a camber distribution, that each point some angle it is experiencing. However, this camber in nature is something this side upper and lower. Third case, we are considering a symmetric airfoil with a distribution function Hx, that is the surface is having a distribution function given by a function Hx. Now, when this airfoil, symmetric airfoil is given with this camber with an angle of attack alpha naught, then it leads to this kind of scenario. Therefore, individual cases can be superimposed on each other to find out a general case characteristics. In this case, where the airfoil has thickness, camber and angle of attack, the local angle of attack alpha naught alpha x can be written as the alpha naught angle of attack and alpha c x, which is nothing but your camber. That means at any point on this airfoil, general airfoil, the inclination experienced by the flow is written as alpha x is equal to alpha naught plus alpha c x, which is given by this function. Now, upper surface we can write down Cpu is equal to 2 times using again Cp formula. Cpu can be written as 2 times m upon m1 square minus 1, and theta is replaced, which is gradient slope, dyu by dx, this gradient which is nothing but slope, and for a small slope theta can be directly written rather than tan theta is equal to dyu by dx. I am directly writing theta equal to dyu by dx, whereas on the lower surface Cpl can be written as 2 upon square root of m1 square minus 1, and in the bracket minus time dyl by dx. You can see the lower surface slope is all the way negative throughout from the leading edge to trailing edge. Hence, generally what we can write down that to have the expressions for dyux and dylx, we can use the mid chord, the mid plane here, the midline here, which is given as ycx, and I can note it down as that upper surface can be written as the gradient of upper surface dyu by dx is equal to dyc by dx plus dh by dx, that is the thickness distribution. in this case, and this can be written as dyc by dx is nothing but minus alpha x, and this again plus dh by dx, whereas for the lower surface gradient dyl by dx can be written as dyc by dx, and then minus time dh by dx we can see it here. dyc dyl is nothing but dyc minus time this thickness, then we can obtain the lower surface profile, whereas the upper surface profile will be by adding the gradient of yc plus the thickness distribution above this yc, the chord, the mid chord. And then using this we can also note that we have written this, that the local inclination is given as at any point on the upper and lower surface can be written as alpha naught plus camber distribution. That is, I can write down the lift as q1, that is nothing but your gamma by 2 p1 m square, that is static pressure multiplied by Mach number squared. I can write down 0 to c, that is entire chord. I can write down CPL minus CPU dx, and likewise the drag can be written as q1 integral of 0 to c CPL and minus dyl by dx and minus CPU dyu by dx into dx. And hence using the CPU and CPL expression from these two equations, let us say equation number 1 and equation number 2, if I introduce this equation into this, let us say 3 and 4, then I can obtain the final expression for lift as 4q1 upon square root of m1 square minus 1 0 to c alpha x dx, whereas the drag becomes 2q1 upon square root of m1 square minus 1 0 to c, and then in the bracket minus dyl by dx square plus dyu by dx square, and then whole integration with respect to x, and integrating, solving again and introducing the dyl and dyux, what I can obtain by from this and this expression, I can obtain finally that drag will be 4q1 upon square root of m1 square minus 1 0 to c alpha square x plus dh by dx square into dx. Now rather than having the plane alpha, what happens for a geometric arbitrary shaped airfoil if we talk about the average local inclination? And then average local inclination can be given such that like this: if alpha average I am denoting with alpha bar, then this can be obtained as 1 by c 0 to c alpha x dx. This leads to, since alpha is nothing but alpha naught plus alpha cx, whereas if I will do this thing, then alpha c minus this alpha c averaging will be 0, because note down here that in this case if you average it, integrate it full, then upper half and lower half will add up and cancel each other. Hence the finally the alpha c average will be obtained as 0, and that is what it is striking out here, and hence alpha bar will nothing but your alpha naught. Hence the CL can be written as L upon q1c nothing but 2 alpha naught square root of m1 square minus 1 again. Now since alpha has the local inclination becomes directly equal to alpha naught, whereas in the case of drag slightly a different story comes. If you take the square of alpha and then take the average, what you will get it, then you have to alpha naught plus alpha c whole square then average. You will obtain here alpha naught square average plus alpha naught alpha c square average, that is a plus b whole square. It will lead to you a square b square plus 2ab. Using that relationship from trigonometry, I can write down alpha naught square plus alpha c square plus 2 alpha naught alpha c whole average. Now, since alpha c averaging again will lead to 0, and hence the expression will remain as alpha naught square plus alpha c square, both averages. Now, replacing their local values with their average values, what I can obtain here is the drag coefficient as d upon q1c is square root of m1 square minus 1 0 to c, then alpha x square averaging plus dh by dx whole square and averaging into dx. And hence the finally I can write down, since alpha naught square alpha x square I can replace with this expression, and hence the final expression I can obtain of the drag for an arbitrary shaped airfoil with a given thickness distribution as CD is equal to 4 upon square root of m1 square minus 1 0 to c, and alpha naught square, that at which angle of attack the airfoil is kept, and then the camber distribution square and local camber distribution, and then thickness distribution squared averaged dx. These are the general expressions for lift and drag coefficient for a thin airfoil in a supersonic flow, that is arbitrary shaped airfoil. Now, an important theorem of compressible flow or gas dynamics, let us see it. So far we have considered the Cartesian coordinate system which has the linear x, y and z axis, and we said it that if the flow is steady, inviscid, that is the frictionless, non-conducting, and that is no heat generation source are there, source or sinks are present inside the flow field, and the flow is the adiabatic, then both entropy and enthalpy are conserved along the stream lines, that is in the flow field. That is, if I denote the streamline direction as S and perpendicular to streamline along the streamline direction S and perpendicular to the streamline as N, then all these relationship which we have obtained for as such in the form of governing equation, they are not applicable once we talk about the curvilinear coordinate system, such as, which is also termed as natural coordinate system. There, if the along the streamline direction is considered as small n and the perpendicular small n S and n, then those equations can still be applied, but when they are converted into S and n coordinate system. What we said that along the streamlines, if the flow field is steady, inviscid, non-conducting and adiabatic, enthalpy and entropy along the streamlines are constant. What happens that, or what is the condition that across these streamlines, that is the perpendicular or from one streamline to another streamline, what is another condition required to have both entropy and enthalpy constant? This is what defined by the famous theorem known as Crocco's theorem. Let us try to look at this. Consider these two streamlines which I have designated in this figure for you. One streamline is this, which is showing here, and another streamline at some distance in the normal direction delta n, and the direction of the streamline is shown along the S and perpendicular, that is the normal direction along the streamline is shown in curvilinear coordinate n and S. Now, in this streamline, since by definition streamlines are those imaginary lines at any point of which the flow velocity is tangential to them, at this particular point drawing this flow velocity is u, and let us say this fellow is making an angle with your normal coordinate system with theta. Now, in this direction, that is the normal to streamline direction, at some distance away delta n on another streamline with this the value of the velocity field here, at this point the velocity can be written as u plus del u by del n plus into delta n, that is the product of delta n using the Taylor series expansion. Retaining the first order term and ignoring the higher order term, I can write down that is u plus del u by del n into delta n. Now what happens, that is along the streamline direction, since perpendicular to the streamline there is no flow and hence there is no normal component of the velocity is shown at this point perpendicular to streamlines. Hence the only change experienced in the velocity is tangential to streamline direction, which I have shown here u and u plus del u by del n into delta n. Now we can also see the variation of the flow deflection, that is at the inclination of u in delta n and delta s direction can be written as theta plus del theta by del n into delta n, again using the Taylor series expansion, that is this velocity is inclined to this angle. Likewise this delta s over the distance of delta n, this distance will become delta s plus del delta s upon delta n into delta n. Likewise this delta n will become delta n plus del delta n by del s along the streamline into delta s. And with this scenario which is in front of us in a curvilinear coordinate or natural coordinate system S and n, we can also note here that any fluid element which is moving along these streamlines will be having a radius of curvature, maintaining the radius of curvature, or in other words the streamlines have the radius of curvature which can be given as 1 by r is equal to del theta by del s. Now in natural coordinate system, as we said, that one coordinate is along the streamline and another is normal to it. Now in the 2D velocity vector, suppose if u is given as u of theta, that is the magnitude and the direction, that is in the polar coordinate system. If u is where u is the magnitude velocity or speed you can say, and theta is the direction. Now what happens, this u at theta is a function of a natural coordinate s and n, and these governing equations which we have obtained earlier in Cartesian coordinate system are not directly applicable, but you still can apply if you transform those equations using your natural coordinate system. Now rewriting the equation, continuity equation and momentum equation in curvilinear coordinate system, what we can essentially directly write for whole steady inviscid non-conducting adiabatic flow, such that the continuity equation can be written as rho u delta n per unit width, that is perpendicular to the paper. This is constant because mass is conserved, and that is meant by continuity equation. Now the momentum equation along and normal to the streamline can be written such that del u del u by del s is equal to minus del p by del s. Note that this equation has come from your famous Euler equation. What it says, we have seen in governing equation that the dp by rho plus integral of v dv we have seen is equal to 0, and we said this is nothing but your Euler equation. Since this is true for all the integrands, and hence we said it that dp by rho plus v dv is equal to constant, and this we call Euler equations. In the natural coordinate system, if we take the derivative in terms of del s, then we can write down this equation is this, that is rho u del u by del s is equal to minus del p by del s. Note that this Euler equation is valid for a steady inviscid non-conducting adiabatic flow. Now Moving to, and this momentum equation is your S component of momentum equation. What happens? The N component of momentum equation. For this particular case, we can directly use our physics principle, that is the centrifugal acceleration. Suppose any fluid element which is moving along this streamline will experience a centrifugal force, and this can be written as here rho times u square upon r, that is rho v square upon r is nothing but the gradient of that force, and here that is nothing but del p by del n, and hence this can be written as further rho u square del theta by del s. Moreover, the energy equation, since we are also interested in understanding the enthalpy, then this can be written as h plus u square by 2, note down this u is the velocity here, and is equal to h naught. Moreover, one more equation, what we find out, that thermodynamic relation, that Maxwell's first relation, we can write down T ds is equal to dH minus dP by rho. Now differentiating the equation number 5 gives you dH is equal to dH naught minus u du, whereas this, let us say this equation we call at 7. Now 7 and 6 can give you, clubbing these two equations can give you the equation as T ds is equal to minus times u du plus dP by rho plus dH naught, we can write down, and let us say this is 8. Now resolving this equation, writing along an normal to the streamline direction, I can write down T ds divided by del s, then I have to divide everywhere del s, and then I can rewrite equation number 8, that minus u del u by del s plus 1 by rho I have taken common, and del p by del s, and plus dH naught by ds. Whereas second case, that T del s by del n minus u del u du by dn in the normal component case, that is normal to the streamline direction, plus 1 by rho del p by del n, and plus dH naught by dl, and this, let us say this is 9 and this is 10. Now from equation number 3 and 9, that is from equation number 3 and 9, let us say go back and quickly check the equation number 3, which is nothing but our Euler's equation. Using this equation, equation number 9 will give you that this fellow is 0, and since along the streamline we have already assumed that this enthalpy is constant, and hence this term automatically goes to 0. Therefore, by equation number 3, if this is 0, what I am leading with T ds by ds is equal to 0, that is if the process is steady, inviscid, non-conducting and adiabatic, then entropy is also constant along the streamline. Whereas from the equation number 10, we can write down that T del s by del n is equal to minus u del u du by del n minus u by r, and I can write down dH naught by dn, and this expression I can give another variable xi, and then T del s by del n is equal to, can be written as dH naught by dn and plus u xi, where xi is the vorticity, and can be written as u by r minus del u by del n, and which can be written as further del theta by del s minus du by dn. Now xi is equal to, we can write down u by r minus del u by del n is equal to u del theta by del s, and this can be written as minus del u by del n, and this is nothing but vorticity. This is a very famous equation which is known as Crocco's theorem. What it says, that is the variation of this equation is nothing but the variation of entropy normal to the streamline, and it is known as Crocco's theorem. This theorem finds that to have a frictionless flow, for same entropy everywhere, if h naught is constant and the vorticity is constant, then you can have the throughout uniform entropy across the streamlines as well. That is, from one streamline to another streamline, the entropy and will be constant only when you have the h naught constant and the vorticity content is 0 throughout the flow field. This is a famous equation, famous consequence of Krokow's theorem, very useful in gas dynamics. Thank you very much.